I, Vineeta Philip, Assistant Professor of Department of Electronics and Telecommunication Engineering, AISSMS, Institute of Information Technology, present my subsequent video of the subject Digital Signal Processing titled Butterworth Filter Design. Infinite impulse response filter design techniques are all based on converting analog filter to a digital filter. The digital design starts with analog design and maps the analog filter from S domain, that is the Laplace domain, to Z domain, that is the digital domain. It is necessary to approximate the characteristics of an analog filter, as the practical characteristics of a filter are not identical to the ideal characteristics. IIR filter design based on Butterworth filter is explained in this video using BLT method. As you see, the magnitude response of the Butterworth filter closely approximates the ideal response as the order n increases. Two important procedures for digitizing the transfer function of an analog filter are impulse invariant method and BLT method, that is the bilinear transformation method. The design steps include, from the given specifications, find the order of the filter. Step 2 is to round off to the next higher integer. Step 3, calculate the value of cutoff frequency. Step 4, find the transfer function h of s. Step 5, the analog filter can be converted to a DT filter using mapping function such as BLT to obtain the transfer function for the digital filter. So let us discuss an example using bilinear transformation to design a Butterworth filter which satisfies the following conditions. Here h of e raised to j omega is between 0.8 and 1 for omega between 0 to 0.2 pi, and h of e raised to j omega is less than or equal to 0.2 for omega between 0.6 pi to pi. So the very first thing is, from the given specifications we have to identify AP, which is attenuation in passband, is 0.8. Omega p, passband frequency of the digital filter, is 0.2 pi. AS, attenuation in stop band, is 0.2, and omega s, stop band frequency of the digital filter, is 0.6 pi. As you see, here is the characteristic plot for the given specification. The very first step is to obtain the values of ohm p and ohm s. Since we are using the bilinear transformation method, the relation between analog frequency and digital frequency is given as ohm p is equal to 2 by Ts tan omega p upon 2. Substituting the value of omega p and Ts as 1, we get ohm p as 0.65. Similarly, we calculate ohm s and we get the value as 2.75. The next step is to calculate the order of the filter n. It is given by n is equal to 1 by 2 into log 1 upon as square minus 1 divided by 1 upon ap square minus 1, the whole divided by log ohm s upon ohm p. Substituting the values of as, ap, ohm s, ohm p, we get n as 1.3. Let us approximate it to the next higher integer. So n is equal to 2. In step number 3, we need to calculate the cutoff frequency ohm C and is given as ohm P upon 1 upon AP square minus 1 the whole raised to 1 upon 2n. Substituting the values of ohm P, AP and n, we get ohm C as 0.75. Fourth step is to find the poles of H of S, and it is given as Pk is equal to plus minus ohm C e raised to j n plus 2k plus 1 into pi the whole upon 2 by n, where k ranges from 0 to n minus 1. And since our n is 2, our k will take two values, that is 0 and 1. Simplifying pk further and finding poles when k equal to 0 and when k equal to 1 are as seen. So here we are applying in this part the Euler's identity and then simplifying further to get the poles P0, similarly for poles P1. The next we have plotted these poles on a pole 0 plot. And we know that for stability, the poles which are on the left hand side of the S-plane should be selected. So we will take only the poles on the left hand side of the imaginary axis for the calculation of H of S. So H of S is given as ohm C raised to n S minus S1 into S minus S1 conjugate. Substituting the values and simplifying it further, we get H of S as 0.56 upon S square plus 1.06 S plus 0.56. And finally, we need to obtain the transfer function for digital filter. So we use the mapping function BLT, which gives the mapping as S is equal to 2 by T Z minus 1 upon Z plus 1. So in the place of S, we are going to substitute this mapping formula and let us take T as 1 second. So the S has been mapped with Z by the BLT formula of 2 by Ts Z minus 1 upon Z plus 1, and simplifying H of Z further, we come to the final H of Z as 0.56 Z plus 1 the whole square divided by 6.68 Z square minus 6.88 Z plus 2.44. This is the required transfer function to design the digital filter. That's all for now. Thank you for watching and stay tuned for many such videos on important concepts of digital signal processing. Thank you.